Hi, this is Bill for SparkyChannel.com, and it's house renovation time. So come on in, let's fix her up. Today I'm going to be replacing a circuit of old two-prong ungrounded receptacles. This video is for educational purposes only, and only competent persons should attempt this installation. And the first thing I've done here is I've plugged in my ideal transmitter. You see, I actually have an adapter on it. This one comes with 3 prongs, but if you just put a little adapter on it and plug it in, it'll give you the correct reading. This reading means open ground. Right here, that's what this means, open ground, which you would expect because this is an old 2-prong ungrounded receptacle. So you plug that in, it says open ground. And so the next thing I'm going to do is I'm going to use my ideal circuit breaker finder receiver. You see, this is the transmitter, which also doubles as a really good receptacle tester. And this is the receiver right here. Now I'm going to go to the main panel with the receiver, and I'm going to find out what circuit this is on. But not only that, I'm going to find out the whole circuit. I'm going to walk around and plug this in to all the various receptacles, and I'm going to find out the whole circuit that this is on. I'm going to work on one circuit at a time. All right, so this is the receiver. I'm at the main panel. Just take it, turn it on, and it chirps, and the green light and the red light are on. Now, go over all the breakers for relative strength. Do a good job of it. Okay, that indicates for the tester all the relative strengths. Okay, here's the receptacle. Here's the breaker right here. We push that and turn it off. Here we are back at the receptacle. Notice all the lights are off. I have a piece of blue tape above this receptacle, and I'm gonna put a piece of blue tape for every receptacle that I find that is off right now, and that'll mark all the receptacles on this particular circuit. Here's another receptacle in the same bedroom, so I'll plug it in, and this is one of them. So this is a second receptacle on the circuit, and don't be fooled because it has a 3-prong receptacle. That doesn't mean that it's grounded. I don't think it's grounded. It's just someone threw on a 3-prong receptacle at some point. Here's the third receptacle in the same bedroom, and it is off as well. So this is part of the circuit. Now I'm in an adjoining bedroom, and I've found another receptacle that is off. So I've marked it above the receptacle with some blue tape. Here's another receptacle in the adjoining bedroom, which is off, and I have marked it with blue tape as well. And here's another receptacle I found in the adjoining bedroom that is off, and I have marked this with blue tape, so that's a total of 6 receptacles so far. Let's see if we can find any more. Okay, I'm in the master bedroom right now, and I'm finding that this one is also off, so this is the 7th receptacle on this circuit. Okay, this is another receptacle in the master bedroom. It's not part of the circuit that I'm working on right now because it's hot. My tests have revealed that there are 7 outlets on the circuit that I'm going to be changing out. Now I need to find out which one of the receptacles on this circuit of 7 receptacles is most upstream, because that is the position where the ground fault circuit interrupter is going to go. It's going to go on the most upstream receptacle. Now, your first thing you do is look and see which receptacle is closest to the main panel. And 95% of the time, I'm telling you, just as an electrician, that's the way we wire things. This would be my guess. But I also have a very nice tester here. This is the Ideal Sure Test Circuit Analyzer. And what I'm going to do is press this down button. See, we're getting 122.7 volts right now. Good strong voltage. Now we're at voltage drop. Okay, voltage drop is currently 4.9%. Okay, the voltage load is 116.6 voltage load, and the amps is 15 amps. See, I'm testing at 15 amps. Now, I could change it to 20 amps where you get 6.5% drop, and I could change it to 12 amps where you get 3.9% drop. Well, let's put it on 15. This is a maximum load. This is a 15 amp circuit. So this would be like a skill saw. This would be like using a skill saw on this receptacle. So this is a heavy load for this circuit. So what I'm going to do on my blue tape here, I'm going to write down 4.9%, big V, little d, voltage drop. 4.9% voltage drop. And the receptacle that has the least voltage drop should be the most upstream receptacle, being the receptacle where you would want to put the ground fault circuit interrupter. So I'm going to go around, I'm going to get all the voltage drops of all 7 receptacles, and it's going to tell me a story. Testers like this, if you use them enough, they talk to you, they tell you things, you know. So I'm going to just go around and see what's happening with each receptacle. This adjacent receptacle with a 15 amp load is 6.7% voltage drop. This one is 8.2% voltage drop at 15 amps. So I've written that down. This one in the adjacent bedroom is 10.5% voltage drop at 15 amps. This one is 12.5%. This one is 14.5% voltage drop at 15 amps. And here we're at the last receptacle, the 7th receptacle on the circuit, and we have 13.9% voltage drop at 15 amps. This receptacle here, this is the first one I looked at. It's the one that's closest to the main panel, and it has the least voltage drop at 15 amps. If I was a betting man, I would bet that this is the most upstream receptacle of the 7. Before I start replacing receptacles, I should mention that my plan is to put the GFCI receptacle in the circuit's most upstream location. Then I'll install 6 new grounding type receptacles in the other 6 locations. This will give GFCI protection to the 6 downstream receptacles. Let's consult the NEC to see what it has to say about this. Here we are at NEC code 406.42b. A non-grounding type receptacle shall be permitted to be replaced with a ground fault circuit interrupter type of receptacle. These receptacles or their cover plates shall be marked no equipment ground. An equipment grounding conductor shall not be connected from the ground fault circuit interrupter type receptacle to any outlet supplied from the ground fault circuit interrupter receptacle. C. A non-grounding type receptacle shall be permitted to be replaced with a grounding type receptacle where supplied through a ground fault circuit interrupter. Where grounding type receptacles are supplied through the ground fault circuit interrupter, grounding type receptacles or their cover plates shall be marked GFCI protected and no equipment ground visible after installation. An equipment grounding conductor shall not be connected between the grounding type receptacles. The first thing we're going to do is turn off the circuit breaker. Next, I'll do a double check with my fluke voltage sensor. The voltage sensor agrees with the receptacle tester that the electricity is off. So now the task is to remove all 7 of the old receptacles on the circuit. My technique now is to spin the terminal screws off with my impact driver, which leaves the copper wires undisturbed while removing the outlet. Now I vacuum out the old box, which after 60 years can be quite dusty. I'll move to the second receptacle. After double checking the outlet, I'll spin off both of the old flathead screws and pull pull out the old 2-prong receptacle. This outlet is what we call a backstab receptacle. I'll use my diagonal cutters and cut the wires flush with the back of the outlet. After I cut the wires flush, I'll strip new ends on them. This is what the old 2-prong outlet looks like once you've cut the wires. Now I'll vacuum out this box. I'll repeat this procedure for the other 5 outlets on the circuit. The next step is to put wire connectors in all the wires, and I'm going to turn the circuit breaker back on. And then I'm going to make a test with my voltage detector to see if one of these black wires is hot. If it is, that means that this is the most upstream receptacle. Okay, I have the circuit breaker turned back on, and here's my Fluke 1AC voltage detector. I'm going to go ahead and test these various lines. And here we go, right there. This one's hot. That means that this is the most upstream receptacle right here. So this is where I'm going to be putting the GFCI receptacle. So now I'm going to go turn off the circuit breaker. It's a very important step. You got to remember to turn off the circuit breaker when you're working on it. I had to turn it on briefly to do this test, but then always remember to turn it back off. I turned off the circuit breaker, and you see nothing's live now. I'm double checking. On the back of the GFCI, you'll see it clearly designated where the line cable goes. So your hot line wire is going to go to this brass colored screw, and that aligns with the short slot on the receptacle. So we got the brass colored line for the hot, and then for this side, this is where the neutral goes. You see there's a silver screw right there, and that aligns with the long slot. So this right here, the one that tested hot, this is your line cable right here. That's one of the reasons we tested. We need to know that this is the line. So this is the load. This carries the electrical energy into this box, and the load carries the electrical energy to the next receptacle. I'll start with the neutral and put it to the silver terminal. And I'll tighten it up securely. I'm going to want to make all these connections very secure, because even though we started out with 4.9% voltage drop, it got a lot higher as the circuit went along. So now I'm going to put the hot wire in on the brass colored side. I'm going to tighten that up real good. So every connection and try to make real solid. Now we take off the yellow tape here. Okay, so put that right in there like that. Here's the hot wire for the load. Okay, got that tightened real nice. I'm not using the green terminal for the ground wire. So just tighten that down. Okay, so our first receptacle is installed, the GFCI. Here we are at the next receptacle. Put a wiggle lever nut on here. I like the wiggle lever nuts in this situation because they use the absolute least amount of space. So here I'm going to put a pigtail into the wiggle lever nut, and then the pigtail is going to go onto the silver terminal. Goes around the terminal in a clockwise manner, like that. Crimp it down and tighten her up. Okay, so then I'm going to take the black hot conductor, prepared a pigtail, put that right in there, and I'm going to take that and go around either one of these terminals. It doesn't matter, they're hooked together. Tighten it down securely. Here you can see that the continuity of the neutral wires does not depend on the receptacle. If mechanical damage were to occur to the receptacle, electricity would still flow through the neutral wires back to the main panel. And because I also pigtailed the hot wires, in the event of mechanical damage to the receptacle, electricity would still flow to the downstream receptacles on the circuit. So I installed grounded receptacles in the remaining 5 boxes in the same manner. Okay, I'm going to go ahead and turn on the circuit breaker. There you go. Okay, I've got the circuit breaker on now, and here we have one green light. That means open ground. You have to expect that because there's no ground. I mean, this is a proper receptacle because it's GFCI, it's per code and everything. But you just get one green light. That's what you get. So I'm going to take that out. Now I'll plug in my SureTest circuit analyzer and I'll get 2 new readings for each of the new receptacles. The first receptacle, which is the GFCI, reads 4.6% voltage drop at 15 amp load. And that's down from 4.9% before I replaced the receptacle. And the no load voltage is 122 volts AC. We'll be watching the no load voltage to see if that drops at all as we go along. Now the second receptacle now reads 6.5% voltage drop at 15 amp load, down from 6.7% with the no load voltage still at 122 volts AC. The third receptacle on the circuit now reads 8% voltage drop at a 15 amp load, down from 8.2% with the no load voltage at 121.9 volts AC. The fourth receptacle on the circuit now reads 9.9% voltage drop with a 15 amp load, down from 10.5% with the no load voltage at 121.2 volts AC. The fifth receptacle now reads 11.7% voltage drop at a 15 amp load, down from 12.5% with the no load voltage at 122 volts AC. The sixth receptacle now reads 13.6% voltage drop at 15 amp load, down from 14.5% with the no load voltage at 121.9 volts AC. And the seventh and most downstream receptacle on the circuit now reads 13.8% voltage drop with the 15 amp load, down from 13.9% with the no load voltage, still at 122 volts AC. So the no load volts AC really didn't drop as we were progressing along the circuit. Now, after testing to see that all of the downstream receptacles turn off after pressing the test button on the GFCI, I'll place stickers on the receptacle cover plates as outlined in the NEC. The GFCI receptacle gets a no equipment ground sticker, and the grounding receptacles get both a GFCI protected sticker and a no equipment ground sticker. In conclusion, I think this was an excellent project with the benefits of getting rid of the annoying 2-prong receptacles, as well as a couple of non-code old 3-prong receptacles. The voltage drop at 15 amps load was reduced for every replaced receptacle, and the old backstab receptacles were eliminated. I'll put links in my video description for the ideal circuit breaker finder set, the Fluke voltage detector, the ideal SureTest circuit analyzer, the DeWalt cordless or corded vacuum which is very valuable for an electrician who needs to vacuum while the electricity is off. DeWalt impact drivers, Wago lever nuts in the 2, 3, and 5 connector sizes, as well as the variety packs, Leviton Slimline GFCI receptacles, which are 25% slimmer than other brands, and last but not least, Leviton Decora receptacles. Thanks. I hope this video was helpful.